Okay, so hello everyone and welcome to the ICTS string seminar. So today we are very happy to have Dalimil Mazac from IAS, who will tell us about automorphic spectra and the conformal bootstrap. So please, Dalimil, take it.
Okay, thank you very much for the invitation, the opportunity to speak. It's a great pleasure. I always fondly remember my visit to ICTS Bangalore. Hopefully I'll be able to repeat it at some point, not too distant future. And the talk today will be based on a paper that I wrote in collaboration with Peter Kravchuk and Sridhar Pal. That appeared on the archive in November last year. And there was also a simultaneous paper by James Bonifacia, which discussed some related ideas. I should say, by the way, please don't hesitate to interrupt me anytime with questions, anytime there is anything unclear. I guess I have 1 hour, right?
Yes, that's right. But if you need more time at the end.
I'll try to be done in 1 hour. Okay, the talk will be mostly about conformal field theories. And the thing that you should know about conformal field theories is that they're absolutely awesome. They're great for several reasons. One of the reasons is that they are cornerstones in the space of quantum field theories. So, for example, a fairly general class of quantum field theories can be thought of as an archie flow between some UV CFT and IR CFT. So if we ever want to have an understanding of the space of quantum field theories in general, we should first start by understanding the space of conformal field theories. So that's reason number one. Reason number two, which for some people is reason number one really, but it doesn't matter, is that CFTs provide a non-perturbative definition of quantum gravity in ADS. So this is just famous ADS CFT, where we have some quantum gravity in the bulk of ADS, and it defines a CFT on the boundary, or vice versa. Maybe more precisely, when you have a CFT on the boundary, you can think of it as defining some bulk gravity dual. And finally, a reason why CFTs are great is that they admit a very precise and effective axiomatic formulation, unlike more general quantum field theories, for which some axiomatic formulations exist, but they are certainly not as effective as this axiomatic bootstrap formulation of CFTs. So what is this formulation? As I already said, it's sometimes called the bootstrap, this axiomatic approach to conformal field theories. So how does it work? Well, in the first sort of step is to focus on local operators of your conformal field theory. And one crucial aspect of this set of local operators is that their space is a unitary representation of some conformal group. This means that we can label the individual local operators, so the spectrum of local operators, by their scaling dimensions and spins. These things are just some quantum numbers under various generators of the conformal group. Okay, so far things are very general. But the thing that makes this axiomatic formulation really constraining is the existence of a multiplicative structure on the space of local operators. And this multiplicative structure is called the operator product expansion. It means that we can make two different points and multiply them together, and we can expand the result in the complete set of local operators on the right. So there are some structure constants of this algebraCijk sitting on the right. And crucially, this product is associative. So it means we can put brackets in two inequivalent ways, like this. And this associativity of the operator expansion together with unitarity and the action of the conformal group severely constrains the possible spectra of deltas and spins and theseCijk. So that's the basic idea of the bootstrap. And one very long-term and ambitious goal would be to classify conformal field theories starting from these axioms. This is, of course, a dream of many people. It was articulated very, very nicely in the following quote by Alexander Polyakov, who said that I think there are two types of useful equations. One type is human-made. They are invented by people. The other type reflects some pre-established harmony. They can be discovered and not invented. And a normalization group is clearly a human-made thing. It's clearly a smart way of calculating things, but it doesn't have a breathtaking quality of, say, the Dirac equation. The example of the second kind is operator product expansion. They form some beautiful mathematical relations, and I was dreaming in the 70s to have some classification of fixed points based on the possible operator Bragg expansions. The program was a little like classifying the algebras. In that case, you start with the commutator relations, which define the algebra, and then you classify all possible semi-simple algebras. And you arrive at a stunningly beautiful theory, which was clearly discovered and not invented. And finally, he says, and I think it's not excluded that in 3 dimensions, something like that is still possible. Okay, so that's the Polyakov's dream, so to say, to classify conformal field theories from these axioms. But the current situation is quite dire. With respect to this dream, in more than 2 dimensions, we have basically 2 cases. There's like a dichotomy in our understanding. There are free CFTs, which are fully understood. We can essentially learn anything that we want about them. They're analytically solved. But on the other hand, everything else is not analytically solved. So we certainly know that there are many examples of interacting CFTs, such as the critical Ising model, but we haven't solved any of them, except for some weakly coupled limits, like large N limits, but an individual CFT has not been solved, which is interacting. On a more optimistic note, the bootstrap seems capable of isolating interacting CFTs. So here's a famous plot from a paper by Kospoland, Simons, Duffy, and Vicky, where the 3D Ising CFT is clearly isolated by bootstrap constraints. And some people think, including me, that this is some evidence in favor of Polyakov's dream, that the fact that bootstrap is so constraining means that probably there is really some deep mathematical structure which waits to be uncovered in CFTs, and we can use it to classify them. Broadly speaking, there are 2 strategies if you want to sort of fulfill this Polyakov's dream. The first strategy, which is the one that most people have been pursuing, is to simply try to solve the bootstrap equations in the space of CFT data. Of course, this is very hard because there's an infinite amount of CFT data and there are infinitely many equations, but maybe the hope is that one day we'll be able to iteratively implement these equations one by one and converge to the classification of some class of CFTs, perhaps. But there is another approach, which is the one that I'd like to advocate today, that hasn't been really pursued that much, which would be to try to identify some mathematical structure which manifestly satisfies all the bootstrap constraints, right? So we would like to cook up some mathematical situation which is like maybe a black box that automatically spits out CFT data that satisfies all the bootstrap constraints, instead of sort of a priori working in the entire space of CFT data and try to solve the bootstrap equations in this space. And the goal of today's talk is to provide an example of this mathematical structure. So it will focus on strategy, on the second strategy of the talk today. So it will be a toy model of such a structure, which leads to many interacting or chaotic solutions of the conformal bootstrap, or a version of the conformal bootstrap. And the rest of the talk will be about clarifying what I mean by this. The basic idea is that it will be to explain some analogy between conformal field theories on one hand and hyperbolic manifolds on the other hand. So it will be the hyperbolic manifolds which will provide the solutions to the bootstrap, or at least to sort of a toy version of the conformal bootstrap. More precisely, the analogy is between CFTs in d-1 dimensions and d-dimensional hyperbolic manifolds. So the manifold has one more dimension than the CFT, and similarly as an ADS CFT, which is maybe not a complete coincidence, but the talk will not be about ADS CFT. It will be about a sort of new type of analogy between CFTs and manifold and d-dimensional manifolds. The basic reason why such an analogy has a chance to exist is that the same group underlies both sides. The group is SO1, D, which on one hand is the Euclidean conformal group of a d-1 dimensional CFT in Euclidean spacetime. But on the other hand, it's also the isometric group of Euclidean d-dimensional hyperbolic space. So that's the basic reason why such an analogy can exist. And maybe before I show you this dictionary, are there any questions?
Sorry, one basic question, Dalimil. What do you mean by a d-dimensional hyperbolic manifold? Maybe you'll say that.
Good. Hyperbolic manifold is a manifold with constant sectional curvature, which is -1.
Okay, but can I have any topology?
It can have any topology. Yeah. So somehow the individual the different geometries or different topologies will give rise to different CFTs or analog CFTs.
Okay. And in this context, there is some statement about three manifolds, right? Is there?
Yeah, in our paper we focused on two manifolds, but this analogy is definitely more general. So maybe let me just show the dictionary, because you're asking more questions. Bring it low. All right, so here's the basic dictionary, and in the rest of the talk I will explain all of this in more detail. So don't worry if you don't catch everything. But here's the idea. So an individual CFT corresponds to an individual hyperbolic manifold. And what is a hyperbolic manifold? For us, it will be a quotient of the hyperbolic D space. So this is just the upper half space, or you can present it as the unit ball if you wish. And it's a quotient by some discrete group, gamma. So here gamma is some discrete subgroup of G, which is SO1 comma D. So it's okay, and there's essentially a one-to-one correspondence between manifolds, hyperbolic manifolds, and such discrete subgroups of SO1 comma D. Okay, and again, I'll say more details, some more precise statements later on. Now, once we fix such a hyperbolic manifold, we can define the space of local operators. And the space of local operators is just the space of L2 functions on this quotient space. So G is the group, the big group SO1 comma D, and gamma is the discrete subgroup. So this is some nice smooth manifold, which actually for us will be compact. We can talk about L2 functions on this manifold, and that's supposed to be the analog of the Hilbert space of local operators. So basically, as I already said, a local operator will be a specific function in this L2 space, where this X is some emergent spacetime. And again, I'll explain in which sense this spacetime is emergent and how to define it. Then you can ask, what is the Casimir eigenvalue of the conformal group? So this O transform in some irreducible representation of group G, and we can talk about a Casimir, and this Casimir just maps to the eigenvalue of the Laplacian on the hyperbolic manifold. So the spectrum of scaling dimensions essentially becomes the spectrum, or is analogous to the spectrum of the Laplacian of the manifold. Okay, so far so good, but then there is also an analog of the OPE, and the OPE just means we take two of these functions in this space on the manifold, we can multiply them together and expand the result in a complete set of functions, and this defines some structure constants. So we have an OPE. The OPE is clearly associative, so we can do the bootstrap, but to really implement the bootstrap practically, we want to define correlators, and the correlators are just these invariant integrals over this group manifold G mod gamma of a product of these local operators. So okay, this is just the basic sketch of the correspondence, and in the rest of the talk I'll explain all of this in more detail. But feel free to ask about anything now if you're impatient and want to know.
Well, I'm just curious, if you have two L2 functions, the product may not necessarily be L2 functions. So what's that pointwise product formula come from?
Good, great question. It will be for us because all of these functions are smooth on some compact space. So their product, I mean, the function that we'll focus on will be smooth and living on a compact space. And a product of such functions is smooth and therefore also L2. But yeah.
Okay, thank you.
It's an important point.
So Dalimil, are these spaces compact? Both hyperbolic.
Yeah. We'll choose. So G is obviously not compact. It's a non-compact Lie group.
Yes.
But we'll choose gamma in such a way that the space is compact. So and that there are many.
Also, the space in second line is compact.
This space is also compact because G and HD only differ by a compact factor, which is the maximal compact subgroup of G.
Okay. Thanks.
Yeah. Good.
I have a question.
Yes.
So this dictionary is not akin to the normal ADS-CFT dictionary, right? Because you have
Yeah, not really. Yeah.
Yeah. Okay. That's all I wanted to say.
Yeah. That's right.
Is
Okay,
it,
so
just a question. So
yeah, sure.
Isn't G mod gamma finite or?
G mod gamma? No, it's not. It's not. Well, it's a smooth manifold because gamma is some discrete subgroup of G, and G is a Lie group. So G mod gamma is some smooth compact manifold that admits a right action by G, because you can multiply on the right by G.
But for Riemann surfaces, is it finite or infinite?
For Riemann, yeah. For Riemann surfaces, this is a U1 bundle over the surface. Because I'll explain.
Okay,
Maybe.
okay, sure.
Yeah, I'll explain everything for Riemann surfaces specifically in a moment.
Dalimil, can I ask a question? This is Aminda. Hi.
Hi, Ninda.
Hi. TheCijk that you showed, are you going to assume that they are real, or are they going to be real for some reason?
Yeah, okay, that's a good question. They will be, so there will be various classes of functions which correspond to different representations of this of G. For the ones corresponding to Laplacian, you can always choose the FIs to be real functions. And therefore theCijks are always also real, because this is some real function on the manifold. This is some basis of real functions, so these things are also real. But more general, there will also be some holomorphic modular forms playing some role, and for those, theseCijks will not be real.
I see. And you will be assuming things like the unitarity bounds, or will you not need them?
Well, I will not be assuming. Okay. Yeah, I won't be assuming anything. That everything is a consequence of this mathematical setup starting from some hyperbolic manifold.
Hi, Dalimil. I have a question. So this the set of functions Fi, would that typically be a countable set of functions, or would there be a
there's a countable basis for the space. It's an infinite dimensional space, but it is a countable basis.
I see. And maybe I'm jumping ahead, but I mean, suppose this correspondence is applied to, say, a rational conformal field theory. So would you expect this countable set of functions to be just finite in some sense? Or is there some more work?
Yeah, that's a good question. So I'm not claiming that I'm actually defining an honest CFT or a rational CFT. I'm just saying that the equations that the spaces on the right satisfy are essentially the same equations that usual CFTs satisfy, but there are some important differences, which makes the space of solutions on the right slightly different from the space of solutions on the left. The space of solutions on the left are CFT, the space of solution on the right are hyperbolic manifolds, but there's some analogy in the equations.
I see. Okay, thanks.
Okay. Let me keep going, because I think I'll probably say much more about
Dalimil.
Oh, okay. Hi, Rajesh.
Dalimil, sorry, just a very quick question. Hi. Is there will you be defining an analog of spin? Hello.
You're breaking out a bit, but I think you're asking whether there's an analog of spin.
Right. I mean, these are scalar that you have defined so far, right?
Well,
if you want things to transform under the non-trivial representations of G, then you would have to enlarge that class. But at the moment, you will be only working with scalars. Good.
Yeah. Well, I'll focus on the case when D is equal to 2 in the rest of the paper. So that's hyperbolic Riemann surfaces. And for that, that's like 1D CFTs, where there is no spin. But once you start talking about hyperbolic 3 manifolds or hyperbolic 4 manifolds, then the representations will carry both the delta label and the spin label. So it's just like in CFTs.
Okay, so you will then be looking at Laplacians of acting on the space of spin S objects, and okay, but I'm just a little bit this thing that, so when I guess you can still define an OPE on the on this enlarged space of this thing by looking at a pointwise product of things. Okay, good.
Yep.
But anyway, it's probably not relevant for the rest of your talk.
Yeah. In general, all of these higher spin things will talk to each other, just like in a CFT. You know, you can take an OP of two scalars, and it will generate also higher spin things. So you cannot avoid talking about spinning objects if you're already talking about scalars in the cases when they exist, like in more than 2 dimensions.
Okay, good. Yeah.
Okay, so eventually I'd like to use this idea to learn something new about the actual conformal bootstrap. But so far the progress has been sort of in the opposite direction. So what we actually did is that we used this analogy to learn some new things about hyperbolic manifolds. So let me tell you just one of the main results of our paper. So we used ideas from Conformal Bootstrap and this analogy to study the spectrum of hyperbolic manifolds. So let's let X be a closed orientable hyperbolic surface. So now we are in 2 dimensions, where G is some hyperbolic metric, meaning a metric of constant negative curvature. Then you can define the Laplacian to be just this usual contraction of inverse G with derivatives. And then we have the Laplace equation. We can try to solve the Laplace equation on this surface. And this is in general a non-integrable problem. There is in general no formula for the set of eigenvalues of the Laplace operator on such a surface. This is a reflection of the classical dynamics being chaotic. There's some exponential divergence of trajectories, and correspondingly, this is like a quantization of the classical dynamics, and you just cannot solve it analytically. But then nevertheless, there's some discrete spectrum. And what we proved is a new theorem about the spectrum, which is that if the genus of X is 2, then there's an upper bound on the first eigenvalue, the first non-zero eigenvalue, which is this 3.8388977. Let me remind you that of genus 2, there's a 6-dimensional moduli space. And we basically, what we show is that everywhere on this moduli space, there is this upper bound. This is an improvement over a previous result due to Xingtun Yao and Yang, which said that this bound is 4. And in fact, our bound seems to be nearly saturated by a very specific point in this 6-dimensional moduli space, which is known as the Boza surface. The Boza surface is the most symmetric surface in this moduli space. It is the largest automorphism group, and its eigenvalue is this 3.8388873. So it agrees with our bound to, I guess, 4 or 5 decimal places. Okay, so now let me fix d equal 2, as I already did in the previous slide, and let me explain to you the setup. Okay, so first some quick review of hyperbolic surfaces. We start with the upper half plane, which is a complex manifold parameterized by complex number z, and its real part x and y, where y is positive and x is anything. So that's denoted H2. And there's a unique hyperbolic metric on it with curvature -1, which is this, dx squared plus dy squared over y squared. Its group of orientation preserving isometries is, as I already said, SO1, 2, or the connected component of identity of SO1, 2, which is the same as PSL2R. Well, how does this group act? Well, it just acts on Z by Möbius transformation. So this is the presentation in terms of SL2R. ABCD is a matrix in SL2R, and Z goes to AZ plus B over CZ plus D. And for all such matrices, this is an isometry of this metric. Okay, and now to fix some hyperbolic surface, we pick a discrete subgroup gamma of G. So in the rest of the talk, G will be PSL2R, and gamma will be a discrete subgroup of G in such a way that the quotient of the upper half plane by gamma is a compact space. So this is our compact manifold. In particular, from compactness, it follows that its volume is finite. We could also think about finite volume non-compact manifolds, and we are currently doing that, but I won't really have much to say about it in this talk. Okay, and by the way, I'm going to allow gamma to have group elements of finite order, which means that it can be, this quotient can be an orbifold. There could be some orbifold points. Okay, so we have a gamma, and X is this 2-dimensional surface or orbifold. Here are some simple examples. The simplest example of these compact quotients are triangle groups. To define such a triangle surface, you take 3 geodesics in the upper half plane. So this is the boundary of the upper half plane, and there are some 3 semicircles, which define a triangle whose interior angles are pi over n1, pi over n2, and pi over n3, where n1, n2, and n3 are integers. And if these integers satisfy this inequality, such a configuration always exists and defines a nice hyperbolic orbifold. And gamma is just generated by reflections across these geodesics, or more precisely, products of pairs of reflections, because we want them to be orientation preserving, but never mind. Here's a nice picture of such a example. This is actually the smallest one. So the smallest hyperbolic orbifold in terms of area is where n1, n2, and n3 are 2, 3, and 7. And here is the sort of depiction of what the surface looks like. So, because we are only using orientation preserving isometries, the fundamental domain is 2 copies of the triangle, which we glue along identical edges. Okay, then more generally, it's useful to define a signature of a hyperbolic orbifold, which is just the set of numbers. First one is the genus, and the remaining numbers are the orders of the orbifold points. So this signature doesn't specify an orbifold uniquely, because there could be a moduli space for fixed G, but this specifies the topology of the orbifold. So for example, at genus 2 with no orbifold points, the signature would be this, and there's a 6-dimensional moduli space, and there's a special surface called the Boza surface, which can be actually tiled using these 2, 3, 8 triangles. Okay, and the fundamental domain for the Boza surface looks like this. These little gray and white triangles are 2, 3, 8 triangles. At genus 3, there is a 12-dimensional moduli space in the case of no marked points, and the most symmetric surface in this moduli space is the Klein-Quartic. It's a so-called Hurwitz surface, which means it can be tiled with the 2, 3, 7 triangles. So this gives it the maximal possible automorphism group at the genus. Okay, so there was just some examples of surfaces to orient ourselves. And what we want to study is the spectral problem on such surfaces, on general surfaces. The spectral problem can be formulated as follows. So we want to study functions in the upper half plane, which are eigenfunctions of the Laplace equation. So this is the Laplace equation, and which are invariant under action by gamma, right? So functions which are invariant under gamma is the same as functions on the actual surface, and we want to solve the Laplace equation on the surface. Such functions are usually called automorphic functions or mass forms. Automorphic just comes from the fact that they are invariant under gamma. That just means they're functions on the surface. Okay, so that's the basic setup of the problem, and we would like to learn some bounds about these eigenvalues. But we would like to derive these bounds without assuming what gamma is, right? We would just like to have a bound for a general genus. So we just want to sort of fix the genus, and we don't want to actually fix a specific gamma inside SL2R. So some more general bounds. Just like in CFTs, where you don't want to fix your CFT, you just want to learn some general bounds, maybe assuming only having 2 relevant operators or something like that. Okay, are there any questions about this so far?
I have a question.
Yep.
So is there any way you could treat, say, higher genus 2D manifolds in this fashion? I mean, here you're dealing with 0 genus manifolds, right?
No. It's general genus. It's general hyperbolic manifolds.
But you're tiling some 2D manifold with some kind of triangles. So
Well, this one has genus 2, so we are sort of identifying some of these edges, right, in such a way that we get genus 2. This one would have genus 3. In general, you cannot always tile it by triangles, but every Riemann surface, thanks to the uniformization theorem, admits some constant curvature metric, and for genus 2 and higher, this is negative curvature, and for all of these things, the rest of the talk applies.
Okay.
So for all these surfaces, you can write them as H2 mod gamma.
Yeah. Gamma is just the fundamental group. So I mean, H2 is the universal. So every manifold has a universal cover, and the universal cover has to be H2 for genus 2 and higher. And then gamma is just the fundamental group by which you have the quotient to go down to the surface.
Yes, right.
Yeah, thanks. That's a good. Yeah, every manifold admits this presentation, and that's also true in higher dimensions.
By the way, have you thought about the relationship with Clifford's paper that has come out recently, where he talks about deformations of 2D manifolds by higher genus deformations, and he considers the CFTs corresponding to that are dual to all those manifolds, and kind of gets the averaging that you get in random matrix models and things of that kind.
Oh, right. You mean you're talking about a paper by Clay and Nima?
By Clifford Johnson.
Oh, Clifford Johnson. Okay, I'm not familiar with that paper. I will.
Yeah, that's the latest paper that he has written. You can check it out.
The paper from a couple of days ago, right? I saw it and I thought it was cool, but I haven't thought about the relation yet.
Yeah, it's cool. Yeah, thanks.
Okay, so that was the setup, and now let me tell you how the Bootstrap applies to the setup. So as I already hinted before, what we need to have is a Hilbert space and a notion of an OPE. Now, what would be this Hilbert space? The first guess for the Hilbert space would just be the space of functions on the surface, right? As H2 mod gamma is the surface, and L2 is the space of functions on the surface. And let's call it V0. Well, that's a pretty good guess, but it's not the final answer. And the issue is that this space is not a representation of the group PSL2R. Simply because the group doesn't act on the surface itself. The group acts on the upper half plane, but because we are quotienting the upper half plane by gamma, we are breaking the symmetry. So there is no symmetry. The surface generally doesn't have any symmetry by gamma, by SL2R. The right choice is to enlarge the space a little bit. So instead of working with this small quotient, we look at this bigger quotient of the whole group PSL2R by gamma. So this is some 2D manifold, but this is now a 3D manifold. Sorry, I have a picture here, right? This could be done better. So we have a G. G is really just the upper half plane times a circle. The circle is the maximal compact group, right? Because you can write any element of G as a product of a translation, scaling, and a rotation. This is just the NAK decomposition. K is the element of the maximal compact subgroup. And well, in this quotient, we are basically keeping the maximal compact subgroup, right? So the G mod gamma looks like this. It's the surface itself, where at every point we have a fiber that's isomorphic to the maximal compact subgroup, which in 2 dimensions is just U1. In general, it would be SOD -1.
Sorry, Dalimil, can you just repeat why the original one wasn't so good choice?
Well, so we want to have a unitary representation of PSL2R attached to every hyperbolic manifold. And the claim is that this V is a unitary representation of PSL2R. Why? Well, because G acts on this quotient by right multiplication. So maybe let me be more clear. So we start with G, this is PSL2R. To get upper half plane, we quotient by K, SO2. Okay, so this is upper half plane.
Right.
To get the surface, we quotient by gamma on the left.
Mm-hmm.
So now this is the surface, but this one doesn't have any symmetry anymore because we quotient on both sides. We cannot multiply on the left or on the right by anything.
Okay.
But if you remove this, now we can multiply on the right by G, and therefore this space is a unitary representation of the, well, I haven't really explained it's a unitary representation, but it's a representation of G.
Okay, good. Thanks.
So we are like enlarging the space by adding functions that you would sort of generate by acting with G.
Right.
Dalimil,
yeah.
What is the analog of changing the moduli of the manifold? When you do that, what happens to this particular space here? How do you
changing?
Is it encoded in the embedding of gamma in G?
Exactly. Yeah. Exactly. So the moduli correspond to changing the embedding of gamma. So every point on a given moduli space has the same gamma thought of as an abstract group, as an isomorphic, but their embedding into PSO2R is different.
Okay.
They're not conjugates of each other.
And the first space had some some points where things were symmetric. Some you had a big automorphism group. Sometimes some enhancement happened, like this Bolzan surface, etc. Similar specialty you see in this spaces also at that point. Some increase.
So right. The automorphism group is just the
full one, right? PSL2R, I guess.
Yeah. Well, the automorphism group is always finite. The automorphism group of X. That's what you're asking about.
No. I mean, I'm saying when the X has. So what are you calling X? X is the
X is the surface.
Yeah. So yeah, that is finite. But I'm saying when you look at G mod gamma at that particular moduli point, right? Does one see any special thing happening, or because you have enhanced this to admit an action of SL2R, at all points you have some action of SL2R?
Yeah. That's right. You will probably see some. It will play no role in the talk, but you can. I mean, the way you see this automorphism group is that you need to look at a normalizer of gamma inside G. And probably just means that, well, this normalizer will then act on the left, from the left on these constants, but I think but it won't play any role.
Okay, thanks.
Isn't it a three-dimensional hyperbolic manifold, actually?
No, this is a quotient of. It's a smooth three-dimensional manifold, which is a quotient of ADS3. If you want to put a metric on it, it would not have a uniform signature, this metric, because PSL2R is ADS3, and what I'm saying, I'm quotienting by the subgroup of the left. ADS3 is isometric, which is PSL2R times PSL2R, acting on the left and acting on the right. I'm quotienting by a subgroup of the left PSL2R, and there is still the right PSL2R left. Okay, so we have this space of functions on this fiber bundle over X. And well, it's a unitary representation of the group. Well, what is the space? This is the functions from the group to complex numbers, which are left invariant under gamma. So for all elements of gamma, they are left invariant, and that have a finite norm. And this is just the L2 norm on this group manifold G mod gamma. And because this measure is invariant, this is just the Haar measure on G. V is a unitary representation of PSL2R, where PSL2R just acts on the right. Right? So for every manifold, even if it has no symmetry, we just defined a unitary representation of PSL2R attached to this manifold. Okay, so next natural actually. One thing that's maybe will clarify some things is to just decompose this space according to how the maximal compact subgroup acts. So PSL2R contains U1, which is the maximal compact subgroup. We can decompose it into different charges under U1, and we'll find the following. So for example, if it has 0 charge, well, that just means it doesn't depend on the circle direction. So then it's just a function on the original surface. So So functions on our original surface are included in this setup, but there are some further functions in the setup which are not functions on the surface, and they come from higher charges under U1, and these things are just sections of some higher bundles, some bundles with some charge over the surface, right? So there are functions which transform with a factor under the action of gamma. So the one statement you can make is that when you have a function in this Vn, so it's a subspace of V of charge n, then it transforms like a modular form of weight 2n. So F is not necessarily holomorphic in this case, but it still transforms like a holomorphic modular form of weight 2n. Just a section of this, what's the right? It's a bundle of holomorph. There are n0 forms. I think that's the right name. Okay, and now you can ask, how does SL2R act on this space? Well, it just acts on functions as differential operators, right? So you can see that, for example, L0, which is the generator of the circle direction, it just rotates you around the circle direction like it should, d theta. And then L-1 and L1, they either increase or decrease the charge under this rotation. And the point is that the V sort of unifies all of these sections of various bundles over the surface into a single object, which is a unitary representation of PSO2R. And the next natural step is to decompose this V into unitary eraps of PSO2R, which of course have been classified. And here's the complete list of eraps of PSO2R. There's a trivial representation. Then there is so-called principal and complementary series. And finally, there is the holomorphic and anti-holomorphic discrete series. And I will try to explain the bare minimum about these representations, if necessary, to understand the idea. But it's
so. Dalimil, sorry, one question. This n that is subscript for this V, is that the spin?
It's not really the spin. It's just the conformal dimension.
Oh, that's the conformal dimension.
Well, it's a bit tricky, right? Because for principal series, the conformal dimension just shows up in a Casimir. It's not really an eigenvalue of any single generator.
Yeah.
So the Vn, n is just the spin under. Is the spin under maximal compact group, which is also what we call dimension.
Okay.
Right. Well.
Okay. Sorry, the maximal compact is the spin part, right? The dimension is the across. I mean, 1, 1. So 1, 1 part, 1, 1. This is the SO2 part, right? Of SO2, 1.
Well, depends on the representation that you're talking about. But if you're right, if you're talking about, it's like very important to make a distinction between Euclidean conformal group and Lorentzian conformal group. If you're talking about the Lorentzian conformal group, which is SO2, D, then the dimension, scaling dimension, is a part of the maximal compact because the SO2.
Okay. Okay.
So the physical operators in a CFT are not representations of SO1, D. They are representations of SO2, D, and the scaling dimension in that case is part of the maximal compact.
Okay. Thanks.
Okay, so now let's just go through these representations one by one, and let me explain what interpretation they have in terms of functions on the surface. So first, the trivial representation is just constant functions on G mod gamma, so also constant functions on the surface, and these appear exactly once inside V, right? There's just one copy of the constant functions. Then the principal and complementary series, there are some infinite dimensional representations which have a precisely one vector of each U1 charge. So one charge, each charge, U1 charge is the one under rotating around the circle. This is how the generators act. But importantly, there is always a single vector which has a zero charge, so that's just a function on the surface. And the Casimir of SL2R acts like the Laplacian on such functions. So the bottom line is that each such principal or complementary series inside V gives rise to one eigenfunction of the Laplacian, where the eigenvalue is related to the conformal Casimir. And it's a one-to-one correspondence. If you find an eigenfunction of the Laplace operator with eigenvalue lambda on the surface, then you can use it to construct a unit. You can use it to construct a copy of the principal or complementary series inside V. And finally, discrete series, they are lowest weight representations. They don't have charge zero vectors. They have some lowest weights of some positive charge delta, which is basically the scaling dimension. And these things correspond to holomorphic modular forms. So you can take for the holomorphic discrete, you can take the lowest weight vector, and the lowest weight condition translates into holomorphic of the function on the surface. And the bottom line is that there's a one-to-one correspondence between these discrete series guys and holomorphic modular forms of weight 2 delta, where delta is just the weight of this lowest weight here. And similar for the anti-holomorphic discrete, which is now a highest weight representation, this one corresponds to the complex conjugates. So we have some function which is a holomorphic modular form, and we can complex conjugate it, and we get an anti-holomorphic modular form of the same weight, and that gives rise to a highest weight vector of an anti-holomorphic representation. So the important upshot of this is the summary. So we have this V that I talked about earlier and this is the decomposition into unitary eraps of SL2R. There is a trivial representation, just constant function exactly once. Then there is a discrete direct sum over eigenvalues of the scalar Laplacian on the surface. And this one corresponds to principal and complementary series. And finally, there is a discrete sum over holomorphic modular forms, or if you wish, holomorphic differentials, where delta is the weight of the holomorphic differentials. And for each holomorphic differential gives rise to a single lowest weight representation and a single highest weight representation.
Sorry, Dalimil, I thought you had some elements in Vn also in the principal and complementary series. What happened to those? This is V0 that you have written, right?
No. It's the whole, no, this is all of V. So yeah, so you can,
No, I mean C lambda A.
You can take this equation and you can intersect it with V0 if you want.
Mm-hmm.
And then you'll get a contribution from the trivial representation. You'll get a contribution from here, which is this little V0 vector that I talked about here. And you will get no contribution from here because all of these guys have non-zero charge.
Right. No, but I'm saying in the principal complementary series, don't you have vectors with n not equal to 0?
Yeah, that's you do. But those are in principle included in this equation, right? This is.
Where are those in this equation?
Well, they are parts of this. This is the infinite dimensional representation.
Okay, fine.
Yeah, so both sides are infinite dimensional representations, and you can intersect them with Vn if you want.
Yeah.
If you intersect with V0, you'll get contribution from these two parts. If you intersect with Vn with non-zero n, you'll just get contributions from here. Sorry, you'll get contributions also from here and from here.
Thanks.
And now crucially for us, the multiplicity of these discrete series representations can be computed just from topology of the surface. It follows from the Riemann Rook theorem that if you have a surface of genus G and certain orders of orbifold points, then the number of holomorphic differentials is just fixed in terms of this signature. There's 2 delta minus 1 times G minus 1 plus some sum over the orbifold points. In particular, the number of weight 1 holomorphic differentials is just the genus of the surface. So that this fixes the number of linearly independent local operators of dimension 1 in our analog CFT. It's just the genus of the surface. Are there any questions?
Sorry, could you please clarify how you got the discrete sum of the A's? I mean, which lambda A's are selected? I mean,
so
yeah,
the sum over A is the sum over independent eigenfunctions of the hyperbolic Laplacian, and the lambdas are the eigenvalues of the hyperbolic Laplacian, and the C lambda is the principal series representation whose Casimir is lambda.
So, Dalimil, just on that line, I just wanted to clarify. If I understand correctly, the VNs that are there in C lambda A with n not equal to 0, those would be those would be eigenfunctions of the Laplacian, but with a shifted eigenvalue by n square or something. Is that correct? Because
they wouldn't really be functions on the surface, because they also now
they're not functions, but I'm talking of the eigenvalues. So when you say that they are eigenvectors of the Laplacian, you mean you can think of each of these functions of Vn, which are in C lambda A, as eigenfunctions of the Laplacian, except that it's not the scalar Laplacian, it's the Laplacian with an extra n square in it.
Yeah, something. Yeah, something like that. Well, the Casimir is always some differential operator, and it has this piece which looks like that, but it also has a piece which depends on the circle direction. And yes. I think it's not really d theta squared. It's more like dx d theta, if I remember correctly. But basically, you're right. There's some differential equation. Which...
usually it's the difference between the Casimirs. The Casimir of SO1, 2 minus the Casimir of the U1. So that's why I said n square. Usually you can think of the in terms of the lower dimensional. Anyway, never mind. But
there's a second order differential operator that they satisfy, and the eigenvalue is related to lambda in some simple way.
Okay. Yeah.
Okay. So I'm going pretty slowly, but there are many questions, so maybe I can.
Yeah, it's fine.
Take a little longer. But anyway, I think the basic idea will hopefully be clear on this or the next slide. So we have this space, which is the space of basic local operators, even though I haven't really defined position, but I'll do it soon. But before defining what the position is, let me define correlator. The correlator is just this. So correlator of a bunch of functions in this space. Okay, so now let's just look at smooth functions for simplicity. But this is a subspace of V. V has all L2 functions, and this has just the smooth functions. So let's take a bunch of them and let's multiply them together. And their correlator is just the integral of this product, right? So this is some invariant integration on this G mod gamma. And that's a nice definition of a correlator. And now finally, let's define the local operators. The local operators are just coherent states of descendants in the discrete series representations. So let's look at this V, L2 G mod gamma. Let's take a copy of a discrete series representation. So we know this one has a lowest weight, which is a holomorphic modular form of weight related to this delta. So let's just take this lowest weight vector, right? It's some very specific function on the surface or on upper half plane. And now we can take this lowest weight and we can translate it by a group element, just like we would do in a CFD, right? You can take the lowest weight is a primary operator, and it's a primary operator at the origin, and to get a primary operator inserted somewhere else, you just translate it by a translation with some parameter W. So W is now the complexified spacetime. It's just something that parameterizes where we translate. Right? So this is how the group element looks like, and well, this OIW is still inside this discrete series representation. It's just no longer the lowest weight vector. And actually, you know, this translation sort of mixes up the different directions, but
I have a question.
Yeah. Mm-hmm.
Why is L-1 the translation operator? It has not the same relationship with the other L0 and L1 as the translation operator has with the Lorentz generator. So
no, L-1
L-1
is
why is it the translation operator here? It's supposed to be the momentum.
It's the same.
It's supposed to behave like a momentum operator, right?
It behaves as a
momentum operator. It's supposed to behave like the momentum operator, right? If it has
but momentum is a generator of translations, right?
Yeah, that's what I'm saying. So does it have the same commutation relations as the momentum operator with the rest of the generators?
Yeah. It's exactly like you would have in a 1D CFT or holomorphic copy of a 2D CFT. In fact, maybe this will help. This is how L-1, L0, and L1.
Okay.
This is how it acts on the local operators. So you can define OI. So let me just emphasize that OIW is a function on this Gmod gamma still. It's just some more complicated thing because we sort of translated the lowest ways to something else, but everything is still always a function on this 3 manifold. And we can do the same thing for the complex conjugates, but there are some, instead of L-1, we should use L1, and the details really don't matter. And with this definition, you can ask, well, how does L-1, L0, and L1 act on these local operators? And they just act as usual, basically by construction. So W is some auxiliary label, which is like an emergent spacetime that you can talk about because you have an action of the group. Okay, so with this, now we can literally talk about correlation functions of local operators. And it follows from these transformation properties that, as usual, Yeah.
Are there no identifications on W?
Oh, this W has nothing to do with the hyperbolic manifold. There are no identifications. So the space W, the space where W lives, is the same for every hyperbolic manifold. It doesn't depend on gamma at all. It's just like for CFTs. You know, different CFTs are different, but they all live in the same space-time.
Yeah, okay, thank you. Yeah, so W is a complex number.
Yeah, that's right. You can think of it as complex, but you can also just fix it to be real. In a CFT, if you have a CFT in say in 1 dimension or in 2 dimensions, then you could work on Euclidean signature, and then you could complexify, go to Lorentzian signature. But really, this is like a 1D CFT in a complexified spacetime. So W is a parameter on a line which you can complexify.
Yes, thank you.
Okay, and then with this, we can talk about correlation functions. So remember, correlation function is just an integral over the group manifold, and 1-point functions vanish because they have to by conformal symmetry, and 2-point functions of OO and O bar also vanish, and that's a little more subtle, but basically it's because the U1 charge of this is always bounded. You know, these are some. This is like a product of lowest weight representations, so everything in their bounded from below, so it has to vanish. But what doesn't vanish is a 2-point function of an O and O bar, so something holomorphic and something antihomomorphic. And the 2-point function is fixed by conformal symmetry to be the usual 2-point function in a 1D CFT, W1 minus W2 to a power which is fixed by the scaling dimension of these operators. And finally, 3-point functions. Well, the 3-point functions which do not vanish are between OO and O bar. And again, they have this following dependence on W's, and there's some dynamical 3-point functionCijk, which is related to the triple product integral of these holomorphic forms, right? Each of these O's comes from some holomorphic form differential on the surface, and you can compute their triple overlap integral, and theCijk is basically that. Okay, so all these delta.
What was O bar?
Okay, so O bar is just an object inside D bar, because for every holomorphic form, you also have its complex conjugate, which is antihomomorphic, and you get O bar by complex conjugating the holomorphic form and acting with the analogous group element.
So you don't have a W bar dependence anywhere.
Yeah. Good. Well, it's just for convenience. You can trade anti-holomorphic dependence inside the unit disk for holomorphic dependence outside of the unit disk by sort of doing W goes to 1 over W bar.
I see.
And that's what I'm doing here. I mean, that's basically the natural thing to do, because D and D bar are not the same type of representation. So the natural thing to do is to define both O and O bar to be holomorphic in W. And the reason why that's the right thing to do is that then L-1, L0, and L1 act in this way on both O's and O bars.
So then the O's are more like chiral algebra.
Yeah. If that's right. If you only do OPs of O's, that's like taking products of holomorphic modular forms, which just gives you holomorphic objects. So there's like a chiral algebra. But now once you start doing products of O's with O bars, the structure is more complicated.
But still, it has only a W. Well, it has. I mean, naively, it has it has only a W dependence. I mean, like your O with the O bar, OP, the 2-point function didn't have modulus of W1 minus W2.
That's right. Yeah, this is a meromorphic function of W1, W2.
So in some sense, even the O's and the O bars together form some kind of a chiral algebra, if I think of it on the plane as a whole. Is that right?
Yeah. In some, well, it's a bit more complicated because the OPE of O and O bar will also contain the Laplace eigenvalues. So let me maybe go on, and that's actually what I want to discuss now. So
okay.
So what's
I have a few questions. Like the L's that you're the F's are defined in the 2D manifold, right? The F's are defined in the 2D manifold.
Capital F. Yeah, I wasn't very clear about this. Capital F is supposed to be a function on the 3 manifold. So what's a good equation? For example, for the discrete series, here's a. I mean, I skipped many of these things, but here's a good equation to look at. So small f. Let small f to be some holomorphic modular form on the manifold. So it's a function of x and y, right? And let's define this capital F to be this function on the 3 manifold. So there's some extra charge under the rotation. And all the capital F's are functions on the 3 manifold, on the G mod gamma.
And your O's are defined where?
My O's are here. So O, you start with a capital F, which is exactly of the form that I just showed. Yeah. So it's constructed from a holomorphic modular form, and you translate it with this group element. So now this thing is doesn't factorize into some angular dependence and a function of the manifold. It's something more general, but it's still a function on the 3 manifold.
But W is a 2D, it parameterizes 2D surfaces, right?
W just lives in the unit disk always. It doesn't, W has nothing to do with the actual hyperbolic surface. It's just some auxiliary variable.
So this is a bit confusing, but maybe if you continue, maybe it will get clarified.
Okay. Okay, so just about the OPE. Well, the OPE just means take 2 functions on inside V and multiply them together and expand them in the complete set of functions in V. And this has to respect conformal symmetry. So in particular, when you take a product of two discrete series representations, you can only find something which is itself a discrete series representation. That's because they're the lowest weight representations. And here's an example of how it looks like. So if you take two O's and take a product, you can expand it again in the complete set of O's. There are no O bars here, or not, or the principal series. By the way, I haven't defined the O's for the principal series. I've just defined them for the discrete series so far. Okay, in this OP, there are some CIJKs which control the ring of modular forms.
Sorry, Dalimil, why wouldn't they mix with some other type of representations? Because that's not respect. I mean, respecting conformal symmetry just means, you know, you should be able to decompose into representations. Why those particular representations?
Well, that's because the details are a bit technical, but this OPE defines for you a certain G-invariant map from a product of two discrete series representations into another discrete series representation. And then there is a purely representation theoretic question of when does such a map exist? And you can ask it for general eraps on the right. And then you can show that this map only really exists when the erap on the right is discrete series itself. And it's related to the fact that the tensor product of two discrete series representations only contains a discrete series representation.
Okay. But if you were to take tensor product of principal series, it will have other stuff and so on, right?
Yeah. But yeah, we are not doing that. You would need to do that if you want to look at sort of 4-point functions of principal series. But yeah.
So using this, you kind of trying to find a closed subsector of operators.
Basically, yeah. Oh,
okay.
Yeah. In the other channel, we can take a product of O and O bar. And in this case, we'll find either the singlet, which is a constant function, or the principal series. And that's just like a representation theoretic generalization of the statement that if we take a, say, product of a holomorphic form and its complex conjugate, then we just get a scalar function of weight 0 on the surface, and we can decompose it into the complete set of eigenfunctions of the Laplacian, so the scalar Laplacian. But this is like a SL2R uplift of that statement. And the corresponding OPE would have this structure. There's contribution of identity and a contribution of the objects in the principal series, which are, well, this is a sum over the Laplacian eigenfunctions.
Sorry, that funny O has two arguments, W1, W2.
Oh yeah, so this, I don't really want to go there, but that's how you would write an OPE, right? The result of doing an OPE of two operators is something that depends on W1 and W2.
Okay, but the actual operator that is dual to this C lambda A is still a normal operator or ordinary operator, right?
Yeah, no, well, I haven't really defined what this funny O would be for the principal series, and it's a little.
Sorry,
it's not a normalizable state. Like when you. Yeah, I don't think I really want to go there. It's not important.
But this sum here can be written like the sum above, right? Or you have to write it this way.
It can be written like a what? Sorry.
The sum in the first line in the first OPE, where the differential operator acts, and you know the W1 W2 dependence is just in the W1 2.
Yeah, that's right. Yeah, I think so. It's just that now the analog of this guy here would not be a really normalizable state. Okay. Maybe that's the only difference.
Okay, fine, thank you.
But we don't really need that to proceed. Okay, so now we have all the ingredients to constrain the Laplacian spectrum, and the essential idea is just to look at a 4-point function of the form O bar O bar. Now the great thing about such a 4-point function is that in the S channel it has the OOP that is controlled by the holomorphic things, which we can control using the Riemann Rook theorem. So we know how many there are of each weight, and so on. But in a T channel, it contains the information about Laplacian spectrum, right? Because O bar, like here, has a contribution from the identity and the Laplacian spectrum. So let's just apply the usual bootstrap to this 4-point function. Well, in our paper, we actually proved that you can apply the usual bootstrap to the 4-point function, but let me just explain how it works. So firstly, this is some function of the 4 W's, but you can factor out the usual dependence on the Wi's. And then there's a function of the cross ratio, which is some dynamical function depending on the specific manifold. Cross ratio is written here. Oh, by the way, this IJKL is just some label of the diff. So ultimately, what we want to do is we want to take the holomorphic 1 forms, the holomorphic differentials of weight 1, because then we know that how many there are. The number of such independent things is the genus of the surface, and then we will want IJKL to vary over these different holomorphic 1 forms. But so that's why I left this index. But for now, you can just forget the IJKL. It's just O bar. And in the S channel, this G of cross ratio has a decomposition using the OPE in terms of conformal blocks. And these are just the same conformal blocks as you would have in a 1D CFT. And the OP coefficients come from the products of overlaps of modular forms. And in the T channel, there is this prefactor coming from this transformation of this guy. And then there's a contribution of the identity, the constant functions on the surface. And then there is a sum over the eigenfunctions of the Laplacian. And now this time the conformal block is a little funny. It's really the conformal partial wave. It is the T-channel conformal partial wave, and it depends on the eigenvalue of the Laplacian. So if lambda is the Laplace eigenvalue, then delta here, which sits here, is related to lambda in this way. So note that this is invariant under delta goes to 1 minus delta. So it only depends on lambda.
So Dalimil, you were talking about how this operator is non-normalizable. So how do you compute this inner product in the T channel?
Well, this thing is normalizable, right? Because OW is normalizable, O bar is normalizable, and their product is also normalizable. But once you try to expand it in something that looks like a local operator for the principal series, the individual things would not be normalizable. But this thing is normalizable. So
yeah, but you are writing a block expansion, so you're making sense of individual terms also.
No, well, each individual block is perfect. You see, that's exactly why I didn't want to go there, because it only creates confusion. Okay. So everything is perfectly finite, and the only things when non-normalizable things appear is when you try to make sense of a local operator inside the principal series. But we never need to talk about these things in the setup, because we have just local operators in the discrete series, which are normalizable. Their products are normalizable. And this thing is not a contribution of a local operator. It's a contribution of the whole principal series representation and some normalizable vector.
Oh, I see. You don't have to go to the W basis in the
yeah. That's right.
Yeah. Okay. Thanks.
Okay. So then we have this equality between the S channel and the T channel, where in the S channel we just have holomorphic forms, and in the T channel we have the Laplace spectrum, and we can play various games and just basically play the usual bootstrap games, relying on positivity here and here. And well, I'm already quite over time, so maybe I'll just highlight some of the results without explaining all the details. But for example,
yeah, feel free to take more time if you want, if you need. Also, it's a bit late for you maybe, but do as you want, because there are many questions.
That's fine. Okay, maybe let me just highlight some important things. So for example, you can just take this equation and now you can just expand it around chi equals 0. So that's not something we are allowed to do in the bootstrap, because chi equals 0 is the S channel and the T channel doesn't converge there. But in this case, the T channel converges. T channel OP converges around chi equals 0 because everything is normalizable. And you can just expand to some finite order around chi equals 0. And at the lowest non-trivial order, you'll find this sum rule. So it's okay, we construct a sum rule from which the S channel drops out. That's not hard to do. And in the T channel, you have a sum over the Laplace eigenvalues of this function, which is a degree 3 polynomial in lambda times the OP coefficient of the principal series. This thing needs to be equal to 0. And now this is a cubic polynomial, which looks like this. It has a negative region, and then it's positive. And the sum rule then tells you that there has to be at least one operator in this region. By the way, delta is the external dimension of the external law. So is the weight of the holomorphic differential that we are using. And now you can show that every hyperbolic manifold has a holomorphic differential of weight at most 6. So it's either 1, 2, 3, 4, 5, or 6. No, if it has, yeah. So and the weakest bound comes from delta equals 6. So basically, every manifold will satisfy the delta equals 6 bound, which is which in the end we computed the bound to be 44.88835, and then you can compare this bound coming from the bootstrap. Oh, sorry, this is the bound coming from the bootstrap, 44.8883537. And this is very close to the actual lambda 1 of the smallest hyperbolic orbifold. So this is the 237 triangle surface, which is a sphere with 3 marked points, whose eigenvalue is 44.8835. And we weren't able to compute the higher terms because we are much better at bootstrapping than we are at actually solving Laplace equation numerically.
Sorry, Dalimil, just to understand the structure of this equation, you had left-hand side equal to right-hand side there, where the left-hand side is something known, right? Something fixed. Well, it doesn't change with the moduli.
Good. Yeah, great question. So the spectrum is something that doesn't change with moduli, but the C's change with moduli.
Okay.
But what doesn't change is that they're that C times C bar is positive. So that's the only thing that we are using. I mean, of course, right-hand side changes with moduli, so left-hand side also changes with moduli, but its dependence is only here. Whereas here the dependence is both here and here.
So in the bootstrap, you kind of solve, you don't know about either side, but just consistency helps you put the bounds, right? But here you seem to know about this delta m's at least. Is that so? And then what is the structure of this equation? I mean, what do you know and what do you compute? Why is there a bound and not solve, actual solving?
Well, one thing that you can, the minimal assumption is that there exists an O with a certain delta, right? That you can use as the external operator. And there is always such an O with delta either 1, 2, 3, 4, 5, or 6. That just follows from Riemann Rook, that you cannot have a higher gap.
Yes.
Right. In particular, for non-orbifolds, there is always a delta equal 1 guy because it's a holomorphic. There are actually G of them, so more than 0. And then you can do this bootstrap, and then you can ask, well, what is in this S channel OPE? Well, you can just make no assumptions. You can say all integers delta appear. So these deltas are always integers, right?
Mm-hmm.
And that's it. That's really the only thing. That's the only thing that goes into proving this bound.
Okay, nice.
And sorry, Dalimil, you probably mentioned this already, but is there a statement about convergence over the spectrum?
Convergence of the bound, for example?
No, I mean you're summing over an infinite number. You're summing over an infinite number of operators.
Oh, good. Yes, there is for fixed chi, this thing converges. Actually, I don't think we discussed how fast it converges. But it just converges because it's literally a statement of you're computing some inner product in an L2 space, and you're inserting a complete set of you're inserting a basis of this L2 space. So the sum converges.
Sorry, of course, the logic. Yeah. Why couldn't C tildes grow fast enough to overtake?
just because there's this argument that if you have an L2 space and then you can compute an inner product bit of two vectors as a sum over a basis of the you insert the identity in the form of a sum over bra and cat, and this will always converge in an L2 space. Of course, this argument doesn't tell you how fast it converges.
I see. Okay.
For the OP convergence estimates, you need to somehow use the P-channel if you want to know actually how fast it converges. And we haven't done that analysis, but we just know it has to converge.
Okay, thanks.
Okay, so for absolutely general orbifold, we have this bound from the bootstrap, and it agrees very well with the smallest orbifold. And actually, we can also extract the spectrum from the extremal functional. So this is the lowest eigenvalue, and then the extremal functional gives us a bunch of higher eigenvalues, each of which agrees really well with solving the Laplace equation numerically on the surface. Then, okay.
Is it possible to get, do you think you could get like analytical expression for lambda 1 from this approach?
Probably not. No, I've been talking to some number theorists here at the institute, and they're telling me that maybe in some cases there are some, like there are analytic expressions in some arithmetic for some arithmetic surfaces, maybe like for those which come from like SL2Z and things like that. But in general, I don't feel. No, I think that would be quite rare to have an analytic expression. Yeah, actually, the spectrum is supposed to be chaotic, and so there's some kind of repulsion of eigenvalues for large eigenvalue.
But so could there be like an analytic version of this bootstrap?
No, there could be maybe something that you could say at large eigenvalue. If you have some large or small parameter. Yeah, that's kind of related to what Ananda was asking about this OP convergence. How fast do the C's grow in one channel, and what does it tell you about the spectrum in the cross channel, low-lying spectrum? Yeah, I think those are fascinating questions, which maybe some mathematicians have looked at, but it would be nice to make the connection very precise with what we have done in the bootstrap.
So does it, sorry, Dalimil, but doesn't the fact, somehow when you have a bigger automorphism group, shouldn't that give you more mileage in some ways? Like you find the Bolsa surface. So in what you've said, the size of gamma or something doesn't really play a role, right?
Yeah, right. Yeah, gamma. There's no gamma in this analysis. Gamma disappeared. Just like it's like in a bootstrap, right? You want to prove general bounds in CFTs.
Right. So somehow you the point you are picking out is one which has a large gamma. But that's not something. Yeah, you don't somehow. There's no way to kind of diagnose that or kind of. I guess. Put that in some way. I just wonder, these are not global symmetries also. I mean, in CFT, sometimes you think that, there's a point of enhanced global symmetry, then you can sort of get some more mileage, but this is like enhanced discrete symmetry in some ways.
It's just a discrete.
Yeah.
Just a discrete.
Yeah. So
I guess you could totally imagine just putting it as an input and just do this bootstrap in the presence of this global symmetry, and then you would be maybe getting closer to the Bolsa. Maybe, perhaps if this bound doesn't really, or I haven't talked about a Bolsa surface, but if the bound doesn't really converge to the Bolsa surface in this general case where we don't input the global symmetry, maybe you could get it closer by assuming global symmetry. And there's even something even fancier that happens for some of these surfaces, which is this arithmetic structure.
Right.
I'm not really an expert, but there are these Hecke operators, which are like additional discrete Laplacians, and they commute with the usual Laplacian. And I think they probably fit very naturally into this story, where you just need to sort of generalize from representation of SL2R to automorphic representations of this whole adelic product or whatever, but yeah, there's probably a way to do that. But then you would really be able to focus on a fixed arithmetic surface, because these things don't have moduli, like SL2Z, or even the Boza surface is arithmetic as far as I know, or the Klein quartic.
They are arithmetic?
Yes, yeah.
Okay. Yeah, no, in some ways, if you kind of restrict, I guess, your bootstrap to things which have this additional one, and then you find a stronger bound, in some ways, I guess that's good enough, right? So even though you're restricting it, but you end up finding a stronger bound. But
right.
Yeah. Okay, good. Thanks.
Good.
I have a question.
Yes.
So just like as in the random matrix model JT gravity correspondence, you have these chaotic chaotic random eigenvalues with eigenvalue repulsion, and that has a certain representation or interpretation in terms of the JT gravity picture. Does all this have a representation or interpretation in the ADS3 in the bulk viewpoint?
I don't know. Sorry. Yeah, I think it's. Yeah, I think to answer this question, one would really have to understand the connection to actual CFTs much better. Yeah, I should also say that there isn't always chaos. Like actually, the question of whether there is chaos and level repulsion for hyperbolic surfaces is quite subtle. And for example, in these arithmetic cases, there is no level repulsion. So even though the classical dynamics is more or less chaotic, the distribution of spacing is Poisson. It's not like random matrix. But as soon as you change the moduli a little bit away from the arithmetic point, then it's supposed to become chaotic, like with level repulsion. So I think maybe all of this is just like a illustration that the questions about the diagnostics of chaos in actual CFTs is probably much more subtle than how we usually discuss it. So for just the existence of arithmetic chaos for hyperbolic surfaces could mean that maybe there's something similar for CFTs. We just haven't thought about it yet.
Okay, thanks.
But yeah, okay, then finally, these are the bounds at fixed genus that I already advertised, where we have used the weight 1 holomorphic differentials. There's G of them, where G is the genus, and by doing some mixed correlator type of bootstrap using semi-definite programming, we arrived at bounds at fixed genus, which are saturated by Boza or nearly saturated at genus 2 and by the Klein quartic at genus 3, and they somewhat improve on previous best known bounds. There's, for example, the bound by Yao was 4 and 3, and our bound goes down and it seems to be saturated. So I guess that's good. Okay, so that's it, and let me just end with some future directions. So I already initially set up the story for general D, but the actual computations need to be generalized to higher D, and we are already doing that, at least in 3 dimensions. It would be nice to generalize it to non-compact finite volume hyperbolic manifolds. For example, the SL2Z, which has a cusp at infinity, and there's a continuous spectrum with some resonances that actually sit at Riemann zeros. That's some funny connection to Riemann zeta function. I already mentioned the arithmetic cases where there is additional discrete symmetries in the form of Hecke operators. And I think most importantly, one would like to extract some lessons from these toy models for the actual conformal bootstrap. And finally, something that we are currently exploring is basically the fact that this this hyperbolic manifold bootstrap is much closer to DS rather than ADS. And basically, for ADS, the group is SO2 comma D, and for DS, it's SO1 comma D plus 1. And really, for us, it's important that the group is SO1 comma D plus 1 here. So, which is why maybe there's some interesting connection to bootstrapping quantum filter in DS. But yeah, that's it. I'm sorry I went brutally over time.
No, it's okay. Yeah, thanks a lot, Dalimil, for the great talk. So, are there any more questions?
Yeah, okay. Dalimil, can I ask you a question about the last point you in your future direction slide? So my understanding is that it is not known which of these series, or if you need to put all the series, principal series, discrete series, and continuous series in the DS bootstrap, right? I mean, so is there going to be any clarity from your work towards that problem?
Hopefully, it's not. Well, you could ask what is there for the free theory, right? You can just put some free massive theory in the Sitter space, and I guess in that case there is no discrete series.
Right.
If I understand it right. But yeah, you could maybe try to use this analysis to prove that it actually has to be there, but we don't have we don't have such a proof yet.
Thanks.
But yeah, it's a good question. So I think somebody raised their hand. Amin, Nizami?
Yes, yeah. Thank you for your talk. So I had a couple of questions. So the first one, I think a related point was raised earlier, but I was still wondering, this is regarding the first point you've mentioned in the future direction. So for something like, say, minimal model 2D CFTs, where we have the BPZ solution, we have a complete classification. We know what the scaling dimensions of operators are and the OP coefficients. So there, like, is it known, like, I mean, what sort of hyperbolic 3 manifolds you're looking at, and what exactly is the, I mean, is there some understanding of what subset of 3 manifolds you're looking at?
Yeah, I don't think that hyperbolic 3 manifolds will literally give rise to 2D CFTs. They will still give rise to solutions of the 2D bootstrap, but there, for example, there wouldn't be any Virasoro symmetry.
Mm-hmm.
I think.
So you have to impose some other structure.
Something the cool thing about actual CFTs, which distinguishes them from these hyperbolic manifolds, is that they in some sense they play well with both the Euclidean conformal group and the Lorentzian conformal group. Mm-hmm. You can define a space of local operators, which is a unitary erap of the Lorentzian conformal group, which we don't have here. So maybe one way you can think about these hyperbolic thing that I talked about today is that it's like the hyperbolic manifold is like an analog of the field configuration space. Like, so if you wanted to define a CFT using a path integral, right, you would define a Euclidean CFT using a path integral, then the path integral measure would have a action of the Euclidean group. Mm-hmm. And the space that I was talking about today would be like the space of L2 functions on the field configuration space. So it's not exactly the space of local operators. So somehow, it looks like for a CFT, you can associate 2 Hilbert spaces. One is the Hilbert space of functions on field configuration space, which is an unitary erap of the Euclidean conformal group. Mm-hmm. And another one is the space of local operators, which is unitary erap of the Lorentzian conformal group. And a CFT has both of these things, but hyperbolic manifold only has the first one.
I see.
So that's kind of our current level of understanding. But I think it would be sort of nice to see how you have to massage what I did today to get something which also has the Lorentzian group acting nicely.
Okay, thank you. So yeah, one more somewhat basic question. So if you're looking at local operators, the CFT side, which are, say, conserved currents, so let's say the energy momentum tensor, then they satisfy some additional constraint, some Ward identity. So how would that reflect on the functions that you're looking at in the hyperbolic manifold? So because they won't just be smooth L2, there would be some other condition, right? So is there some natural expectation?
it's related to your previous question in the sense that conserved currents, they're representations of the Lorentzian group. They are not representations of the Euclidean group, really. So conserved currents literally wouldn't really appear here. But for example, a close analog of the word identity is this fact that modular forms need to be holomorphic. That there are some lowest weight representations here, and they satisfy this lowest weight condition. So this is a bit like conservation of the current. So this implies that the function on the surface is holomorphic, but it's just an analog. It's not literally, it's not the same representation of the conformal group that's being described.
I see. And so if you're looking at, for example, a fermionic local operator, then would you be looking at the spectrum of some Dirac operator, or is it still some Laplacian?
Oh, good. Yeah, so there is a way to talk about a Dirac operator, I think, here, which would be just to allow half-integer charges under this U1. There was this important U1, the maximal compact group.
I see.
And if we take a half-integer charge under that one, that's like going from PSL2R to SL2R. So you're introducing spin structure on your hyperbolic manifold. And I think everything will basically generalize just by including a few more representations into the game, and they correspond to the spinners.
Thank you very much.
So Dalimil, I have a question. So in this case, it was important for you to have this kind of decomposition principal series, discrete series, and the discrete series kind of played an important role, right, in defining the OP. So in higher dimensions also, is there a similar type of decomposition that is known? Because these were related to some modular forms, etc. So I was wondering if the similar structure, holomorphicity is not there.
Right, good. So you can always define V in the same way. It's just G mod gamma, space of functions on that. Yeah. And you can always decompose it into eraps, and then you can ask, well, what is the set of eraps for a given, like for example, for SO1,3, there's basically just the trivial representation and the principal series. There is no discrete series in that case. But there are still some connections to topology. For example, when you think about so now principal series for SO1,3 would be labeled by dimension and spin. And when you think about the spin 1, at the center of so the principal series is like 1 plus IT. So just take the 1 plus 0t. Those guys correspond to generators of the first cohomology. Again, their number, the number of such independent things, is the first Bethe number of the manifold.
Oh,
so it's kind of similar to these. Similar to we had a G number here was the genus. This just becomes the
interesting
Bethe number. It's not holomorphic, so you don't have this nice holomorphic structure, but you can still basically play the same games.
And also in the principal series part here, as you say, it is labeled by some continuous number, right, on the imaginary line. So here on the right hand side, you still had a sum over these things, but should you not have an integral?
Well, so a priori, the principal series is a continuous set, but you fix your hyperbolic manifold if it's compact. That selects some discrete subset of that, which is the subset appearing here on the right. If it's non-compact, then there's a continuous spectrum, and then there's the actual integral.
Okay, I see.
Which may have poles, and then maybe you can ask if you can deform.
I see. That's how it relates to probably usual ADS CFT.
Yeah, that would be great if one could make that more precise.
Okay.
Yeah, I think one basic issue is that all of these Hilbert spaces are way too small to describe anything like a physical CFT. Like they are in a physical CFT, the growth of operators is very fast. It's like Carde, from e to the delta to some power, and everything here it grows more like polynomial with delta. So I don't think it really has a chance to really become like a construction of CFTs. Yeah, actually, you know, I should say that one of the things that inspired me to think about this was your paper about what's it called? Is in search of conformal theories. So that's kind of the, you know.
Nice. Thanks.
I have a question regarding the the relationship between the OI.
I think you maybe got muted.
Oh, did I get muted?
Yeah, I didn't hear. I can hear now.
Okay.
Yeah.
So the relationship between the OI omegas and the FIs, and you got the OI omegas by applying a translation operator on the FIs, right?
Mm-hmm.
So the FIs were defined on the three manifolds, whereas if you apply a translation operator on some operator on the three manifold, how do you get something which is a two-dimensional operator?
So it's everything is a function on this G mod gamma. So what G mod gamma is it what we are calling three manifold, right?
Mm-hmm.
So everything is a element of this of G mod gamma. You know, this is one such thing, and this just translates it inside this space. So it's just some action by G. So I'm not sure if I'm answering your question, but
yeah, the question is, I understand it's a translation by G. I mean, it's a translation inside that manifold, but Y omega should have not only dependence on omega, but also the dependence on the variables that Fi depend on, right? Because it's a function of all those variables. How can Y omega be dependent?
Yeah. Okay, yeah, sure. Good. Yeah, that's right. You're absolutely right. I'm just suppressing those variables. I'm just thinking of this as an abstract vector in this space. Right. So for fixed W or omega, for fixed this number, this thing is just an element of this space. And indeed, elements of this space, you can think of them as functions of three variables, but I'm just suppressing those variables here.
But then when you consider the operator product expansions of the OIs, wouldn't those variables also matter in some way?
Yes, I mean, then the product would, the product here. So this is a function. This is a function of three variables. This is a function of three variables, and you take a product. It's just a pointwise product in those three variables, and you're expanding that in some way. But, yeah, I mean, it matters in the sense that that's the underlying structure of these objects, but you never have to. The validity of this equation doesn't depend on the details of those functions. It's always true, just thanks to conformal symmetry. It's just like an identity between abstract vectors in that space.
So are you keeping those extra variables fixed when you consider this particular expansion?
Yes. This is a pointwise product.
Okay.
Or fixed, yeah, the same. Yeah, that's right. I mean, yeah, it's just F1 at X, F2 at X, and now we're expanding it in Fi at X, all at the same position on both sides. Yeah, that's an important point. Thanks.
Dalimil, one last.
Yeah. Sorry. Go ahead.
So one last question. So from me is this? You had some statement about the general structure of the spectrum, right? Could you elaborate on that? You had some continuum and then some discrete stuff and so on. Why should the spectrum be the way you propose?
Are you asking about this equation?
There was some there was some picture of the spectrum, right? With some.
Okay. This.
Yes. What is this? Yeah.
Okay. Yeah. Good. I didn't discuss it. So this is a. So you can ask the question if you scan over all the hyperbolic two manifolds, and you ask what is lambda 1
of a fixed topology, or not necessarily.
All
Okay.
topologies, just scan
Yeah.
over all topologies and all moduli.
Yeah.
And then you have a map from
Okay.
the set of manifolds to lambda, to the positive real line, which is the map called lambda 1.
Okay. Okay. I see.
And you can ask, what is the image of this map?
I see.
So we basically proved that this is the image, that for there is a set of isolated points. The 2, 3, 7 triangle has this gap.
Okay. Okay.
Then there's nothing. 2, 4, 8 has this gap, and so on. And then there's a continuum starting for the first one that has moduli. That's a sphere with 4 punctures.
I see.
So
not a statement about the spectrum, but rather lambda 1. Behavior of lambda 1 in the space of surfaces.
It's a set of lambda 1 when you scan over manifolds. Yeah.
I see. Okay. Thanks.
Those numbers, are they algebraic integers or they're just? By this I mean their solution.
They are definitely not algebraic integers. I think they are basically not known to arbitrary person. There are some transcendental numbers that.
I see. So you got those numbers, they're not the solutions of some equations. You just got them from numerics.
Yeah. You can either get them by solving numerically the Laplace equation, or now apparently you can get them pretty accurately from the bootstrap.
I see. Okay. Thank you.
Sorry, Dalimil, but if you go to some symmetric surface, some Bolzan surface or something, and then you move, not Bolzan surface, so this 44 point, this thing, right? So that is probably some symmetric point in the modular space. Now, if you move away a little bit, then wouldn't you explore the neighborhood of that?
Yeah, this one doesn't have moduli. It's a sphere with 3 punctures.
Oh, I see. That's why they are rigid. All these things are rigid.
Yeah. So yeah, the only things which are rigid are spheres with 3 punctures, and you can see that they appear. This is all of them. The first number is genus. And
thanks.
Good. Actually, surprisingly, this one there's both a sphere with 3 punctures and sphere with 4 at the same. I think one covers the other or something like that. So they have the same.
Actually, why did you restrict to hyperbolic manifolds? Isn't it more general for anything of the form like G mod gamma for suitable G and gamma?
Yeah, that's a great question. So yeah, you could try to do this for general G, for general semi-simple, or not even semi-simple, just a general, let's say semi-simple E group. Then there's something special that happens for hyperbolic manifolds. So hyperbolic means that the G is a SO1, D. And for this group, something special happens, which is that the tensor product of 2 eraps like the tensor product of 3 eraps, the spaces of intertwiners are finite dimensional, is the right statement. And that's something that doesn't happen for other groups, at least for general representations. Yeah, for SO1, D and
do you need this?
Sorry?
Do you need this for this bootstrap?
Yeah, we need it. But, well, for SL2R, the space of intertwiners is 1-dimensional. And that basically just shows up. That just means that this OPE is uniquely fixed by this set of numbers, CIJKs. If it's not finite dimensional, then for each 3 eraps, you would have infinitely many CIJKs, and it would probably be harder to implement. Maybe impossible. I don't know. We haven't. Even for SO1, D, where D is greater than 1, this number of intertwiners is greater than 1-dimensional. Like this is this fact that the number of tensor structures sort of grows. For spinning operators, there are multiple possible 3-point functions. Yeah, but apparently for other groups, it's not even finite dimensional.
Okay, thank you.
Maybe it doesn't. Maybe it can still be done. I don't know. So.
Any more questions for them?
Sorry, along the similar lines, the previous question, if instead of computing eigenvalues of Laplacian, if we were to compute some other eigenvalues of some other system with some, let's say, background gauge field or something, so essentially computing eigenvalues of some, I don't know, but I'm saying these types of questions probably could also be approached, right, with more complex systems, and then you would maybe have some global symmetry laying in or something like that, just very vague, very vague. If you have some bundle and you want to look at the spectrum of the sections of that bundle.
Yeah.
But here the whole story is basically representation theory, right? Or not?
Well, in this formulation, yeah, but you could sort of forget about. Actually, yeah, that's how these other papers were written. That's a paper by Hinterbichler and Bonifacio. They didn't have this connection to representation theory. They were basically just starting from differential equations.
Okay.
And then the representation theory is sort of hidden in integrating functions on the surfaces and integrating by parts and seeing how covariant derivatives commute with each other. But you could just, actually the original paper was on Einstein manifolds where you don't have any group acting. It's just a question of what basically a special case of what you were saying, Abhijit, some differential equations and playing some games with integrating by parts.
These guys are geometers or physicists?
They're physicists. Yeah. Okay.
Yeah, thanks, Dalimil. It was wonderful.
Thanks.
Yeah, thanks a lot. I guess it must be late for you also now.
Oh, it's almost 2.
Yeah, thank you for talking so late.
Yeah,
No
thanks a lot.
I never got so many questions after this during this seminar, so it was great. It was really fantastic. I could.
Yeah, thank you so much. It was a great talk.
Thanks.
Bye.
Okay, so let me end the meeting now. So, bye.
Bye.